All right, guys, let's get started. So, got white space there. Any questions before we begin? Anything? Any issues? Anything? All right. So we are currently on week 4, right? So keep that in mind. The first exam is going to be on week 6, so that's in about 2 weeks. So hopefully you're studying through the material. So far, we've covered confidentiality, we've covered integrity, we've covered hash functions. Today, we're going to cover block ciphers and modes of operation in more detail, and probably get into DES, the data encryption standard. So that's essentially like, the first third of the class is, those block cipher algorithms. Okay. So that's what's going to be on the exam. Exam 1, anything from the labs, or anything from the notes. Okay. Today I'm going to do like a little short quiz for the participation that you guys have in your syllabus, about 10% of your grade. It'll just give you an idea of the, a type of a problem, right, that you can imagine could be on the exam, right? So the exam is going to be about 10 questions, 10 problems. It could be essay type question. It could be, write 20 lines of code or less, right? It could be just explain this or something like that. Does that make sense? So they're like essay type questions, but they could be problems or code, etc. All right. Any questions about that? All right. So, you take it in class. You have to come to class. You'll download a Word document, do everything on it, and then you just upload it back to Brightspace. Okay. All right. So remember, so that's going to be exam 1. Once we finish this set of topics, we're going to move into something very interesting that I think you'll find very fascinating, which is asymmetric encryption. So that's going to be RSA. The whole point of that is going to be exchanging that key, right? So we're going to look at that, but that's coming up probably at the earliest next week, if not week 6 during the week of the exam. So the exam is going to be on that Tuesday. Okay. So that's the idea. I started grading your assignments. So I haven't finished all of them because it takes me some time. Some of you have a grade, others don't. But in the next couple of days, you're all going to have assignment 1 graded. And yeah, so today we're, the quiz is interesting. So I think, it's just to get you to see the tricks that I can play on you on the exams, right? So, but yeah, should be fun. Remember, there will be also a practical exam sometime around between week 8 and week 10. And this is a whole lab session that I call the scavenger hunt, where I'm gonna encrypt a secret, but it's gonna be behind like 8 encryptions. So you have to break one encryption and another until you actually get, and it's going to be everything that we've covered. All the, it's everything like the scripts that I provide, it's all going to be based on that, obviously. Make sense? So I always do like, what do you call it? Like before a trial run, I guess, before that actual practical in class, so you guys can see how it works. All right. But anyway, so just keep in mind, this class goes into a lot of depth and everything built on previous ideas. So, make sure that you're understanding everything. All right. Any questions before I begin? Nope. All right. So kind of where we are right now. Last week I spent some time on XOR, right? So that was the main objective. Gave you XOR as Python code. We even implemented an XOR hash algorithm. So you have that. I believe I do have a pseudo-random generator code that I will do sometime this week. But yeah, the topic today is essentially block ciphers, and we're just going to go through all the details of that. Hopefully all the way to like DES, the data encryption standard. which, by the way, has been broken already, right? We use AES today, but you'll still see that it's quite a complex algorithm, even though it's broken by brute force. But it's interesting how it was, how what happened historically. So we'll talk a little bit about that. Let's take a look at bright space for a second, just to see where we are in the modules. This one. So we've completed this one, right? Hash functions, XOR. Those are completed. You can see exam one is kind of coming up here. RSA kind of happens, yeah, somewhere around it. And this should be the module for today. So I'm pretty sure, yeah, so we've covered this. These are the OpenSSL hash examples that we did. So now we are here. Oh, yeah, go ahead. Oh, yeah. Right. That's a good question. So I should have said, so the exam is closed notes, but you're allowed a cheat sheet. You can use one of these 8.5 by 11, both sides, and you can write whatever you want on it. That ties into that, right? Write everything down in here. And you can have code examples, algorithm examples, definitions. I like this system because I know it, and you're transcribing all of that. At least you're reading the notes and passing it on, right? So that's a good way of studying. It's going to be things I've done in class. So it's not going to be anything mysterious or anything like that. I might do a little trick here and there, but it's pretty straightforward. Okay. So a lot of understand the algorithms, I would say, like, understand the algorithms that we've done. Hopefully XOR makes a lot of sense. It's pretty simple. You need to understand confidentiality, integrity. There will be some questions. I think I said this, like you go to a Starbucks and somebody has their bank dashboard open. You look at it, but you don't do anything to it. Which of the pillars has been affected? So confidentiality, right? Because you looked at it, but you didn't do anything. Do you see that? So there will be a few questions like that. But yeah, you're allowed a cheat sheet. Any other questions about the exam? Nope. All right. Great. So I think we were discussing this module, as you can see. So I have it in here, XOR. XOR is a big component of block ciphers, so we're going to continue to use it. Symmetric encryption, remember that's the topic that we are currently focused on, and that is the XORing types of things. And then the data encryption standard. So my goal is hopefully today to get to discuss that whole algorithm. Okay, discuss that whole algorithm, and you will see, that there's no real mystery in it. If you understand XOR, then there's a couple of things that are happening that are very interesting. So I have some code here to the GitHub. I have, the homework. This will be on Thursday, of course. And then I have this DES Feistel network. So these are my notes. So it's basically what I'm going to discuss today. So just for your convenience. But yeah, the Feistel network is essentially at the heart of the data encryption standard. And it's just some logic. That's all it is. To scramble the data, in different ways, right? But you're still using XOR as the underlying operation, and you'll see how you're just adding complications. It's like if you've ever heard of that term, right? Like you just add a complication so that it takes longer to get to the data, so you have more steps to get to the data. So it's essentially like that. Okay, but we will definitely see the Feistel network, and I think it should be pretty interesting how that works. Okay, so the problems that we will do, so you can see some problems that we will talk about, Python related. So here, implement in Python the CBC algorithm, for instance, right? So we will see that. So remember CBC, ECB, those are modes of operation. You've already used those, right? And then you've seen how sometimes you do AES and then you say mode of operation CBC, right? So you can use different modes of operation within an algorithm. So there's two things there. It's easier to just focus on implementing something like CBC versus implementing the whole of DES. That's kind of complex. And AES, which is the current one, is even more complex, like even more. Okay. All right. So that's kind of just to give you an idea of the materials for the lab assignment on Thursday. That'll be mostly a coding thing, but today I'm just going to do lecture. But just going to give you an idea. It's kind of here, and you can see we're getting close to exam one. So I might move RSA a little bit here. We'll see how we move. All right. So I'm going to switch over to the whiteboard. And we're going to use this for all the diagrams. But we're going to talk about symmetric encryption and block ciphers again, right? So this is the topic. Block, change this to red. Block ciphers. And we're just going to go over some common things in the block ciphers. You've already seen the code, right? I took that message and I created a list of blocks, right? So that's essentially the idea. Blocks of 8 characters, I think it was. So that's what we're talking about. And then all those blocks have to be XORed. And that's essentially the encryption. Another term that we have, of course, is modes of operation. So we have modes of operation. Okay, and that's going to be your ECB, CBC, and so on. And you guys understand this from the images that one is insecure, the other one is more secure. So these are essentially different ways of breaking up the message and XORing the blocks. That's essentially the idea. So I'll remind you that the underlying problem with ECB was that we have, a plain block 1, and we XOR it with the key, right, to produce a cipher block, C1. But then we have plain text 2, the other block, XORed with the key, and this creates C2, and so on. So what's the problem? The key is the same, right? So if we have 2 plain text blocks that are the same, what's going to happen? The cipher, it's also going to be the same. So that's essentially the problem with the ECB or electronic codebook. So we're going to say that if M1 is equal to M2, then C1 will be equal to C2, right? And that's a problem because that's how we can figure out that there's still a pattern. And we saw this with the images. Okay. So this can be very insecure. That's the electronic code book. So if the attacker is able to intercept these 2 blocks, C1 and C2, and they're the same, right? They can start to infer some things about the message itself, right? So I gave you a problem, right, that you guys, for bonus points, if you want to work on and solve it, right? So we did the example of images. So imagine we have an image here. We have an image, and the image has, just some values. Let's do like a grid. Right? So if we have, let's say A's for whatever reason, once we encrypt these A's, while they may become another um, set of values, they still will all be the same. And that's the downside. So in this case, let's say this would be 111. This would be 111, 111, 111, 111. So you guys can see that it's almost like there's a shape that is maintained, right? And this is the example that we solved. So the pattern may persist, and that's the problem. Okay, so then what we need to do is we need to look at other modes of operation, such as CBC or the cipher block chaining, right? So this is another mode of operation that might be better than this one over here. Okay. So let's talk a little bit about CBC. And this, as I said, is an algorithm that we will implement. So essentially, we'll use the code from last week, and we're going to just extend that a little bit to make this work. So CBC stands for the cipher block chaining. Cipher block chaining. So again, the process, the plain text is going to be divided into blocks, and each block is XORed with the previous block to get the ciphertext block. So that's essentially the key. This is where we now have an initialization vector, IV. So the message is made unique by introducing a previous block, right? That's being used in the encryption. So we're going to see this one in a diagram form, CBC, as this is, as I said, make sure you understand how this works because we're going to be implementing this in Python this Thursday. All right, so let's take a look. So this will be CBC. So here I have a message, right? So I have a plain text message, M, make it a long one. And I'm going to split this into blocks of equal size. So these are going to be my plain text P1, P2. I'm just going to do 3, P2, and P3. For example, or I should say PN probably, and ... but it's the same, right? So there's several blocks. So the block comes in, and it's going to be XORed with the IV. Remember, so we have this initialization vector, right? And just so that we have some previous thing that we can use for the XORing, so we need an initial vector. Here, the initialization vector is not the secret. The secret is going to be the key, okay? But it's something that you need to pass, and this is why you're doing the exercises with your classmates, right? So you know that if you don't send that, it's not going to work. Remember, ECB does not need an initialization vector. So here, then, I have a block cipher encryption. Let's say here, let's just say another block. So this is now like a temporary cipher. Let's call it the cipher 1 temporary, for instance. And then this one is going to be XORed with the key. Okay, so the key comes in. So we will have to do this double XORing on Thursday in the code, right? Once that's done, this will produce the actual cipher. So this is what you would save in a list and send to your partner so that you can do the encryption correctly. And this would be a much better cipher for achieving confidentiality. All right, now the key thing is this is the plain text message here. Now you can see the algorithm comes in, you do an XOR. You need something previous. So in the past, we used div, but we don't want to use div here, right? That would be like the same mistake that we were making before. And so what needs to happen is the cipher itself, C1, is going to be passed to this step, all right, instead of the initialization vector. Okay, and this comes out, and we have now, of course, an XORed output, which I'm going to call temporary cipher 2 or some name like that, block cipher encryption. And then I'm going to give it the key. Okay. And remember that when we do these things, we have to do this both forward and reverse. And that's actually the trick or the little quiz that I'm going to give you today is that, forward and reverse, we have to think about that, right? There's some patterns, but we just have to there's some differences as well. So here I'm just going to plug in key over here, right? And then this, of course, sorry, it's like I'm running out of room here. I'm going to produce cipher 2. So we'll call this C2, and that is the actual cipher for that particular block. Does that make sense, guys? So this is what you sent to your friend. Let's say here, I'm going to put this in blue. So I'm going to like maybe mark it. So this one and this one, right, are the outputs that you would send over the insecure internet to be able to communicate and send the message. All right, let's do the next one. Okay, so I'm going to switch over to red. The last part then we XOR, right? What is the input to this one? So the same thing. This would be the C2 becomes the input for P3. This produces another temporary block. Okay, so that's going to be, let's say, TC3. Now we're going to do another XOR here of the key. Okay, and that produces the final C3 cipher block. And that's essentially, once we get here, we have a somewhat secure algorithm. Okay, so this one also, mark it in blue, right? And that's another one of the blocks that you would send. So now you send this to your friend, they receive it, and now they have to decrypt it. And notice that they have to have the previous block. So how are they going to do that? Do you see that? You see how you're producing a block and then using it for the next encryption. But now you guys have to do that in reverse. Okay? So that's the idea. So that's something that we have to address on Thursday, right? How do we go back and forth? All right, and then there are other diagrams. So they're all pretty much the same. You can imagine how you could start with, instead of starting with the plain text here, you could have started with the initialization vector, encrypt that with the key, and then proceed, right? So what that means simply is there's different orders that you can have. So I'll just give you a very brief example. So another mode of operation, CFB, which is another one that you have seen, it's similar, right? But just a slightly different logic. You might start with the IV, right? You might start with that one, and then the IV gets the key. So I'm just going to say key here. And that produces another temporary cipher block, 1, let's call it. And then after that, you introduce the plain text. So P1, and that gets XORed. So you can see it's literally the same thing that you're doing, but you're changing a little bit the order or the pieces that go in and out. And they have there's different reasons why they've done that. So this is cipher 1, and that would be the block that we want to use. Okay, and then as before, this one is a little bit more interesting because now this cipher block, right, becomes the input to the whole thing. Do you guys see that? Becomes the input to the whole thing. So that's why this is more of a stream type of an idea, like with the stream cipher, because it's just like you generate it and then that becomes the input. And then so this is a block, essentially, this same block gets XORed with the key. You can see that there. And then you come here and then the plain text message comes in. This would be P2, right? So this is P2 comes in here, and now that produces C2, right? C2. And then this one becomes, let me complete it here. Now this one becomes the input to this whole process for the next iteration. So just keep this in mind. On the exam, we're gonna do the Python code for CBC on Thursday, and I might on the exam the question might be implement CFB instead of CBC. So you have to just be aware of the difference. Any questions on this, guys? No questions? Does it make sense? Yeah, please go ahead. EC1 just means it's a temporary cipher. So if you think about it, right, you take a block of zeros and ones, that's the IV, and a block of key, and you XOR them, you're gonna produce a new block, right? Yeah, and then that block, that's why I'm calling it temporary, and then that block is going to be XORed with the actual plain text at that point to produce the cipher that you want. And that's actually the part that you would send to your friend. And then, but that also becomes the input for the next block. You XOR it with the key, right? And that produces, and I guess here I didn't create that. So this is probably what you guys are talking about. So here, right, I should have, to be consistent, I should have produced the block. What would this block be? TC2, very good. Thank you. TC2, exactly. So it's just, that's why it's good to see this in code, because in code, you can't skip things like this. It's gonna break. But we'll look at that on Thursday. And then P2 comes in, becomes C2. Then I guess I can do one more. So this block comes in, and then you have the key again coming in. Key goes in, and that will produce TC3, temporary cipher 3 is what I'm calling it. And that takes in another XOR operation where you have P3, which is the next block of the plain text message. Got it? And then that then produces C3. But once Bob does this, sends it to Alice, now Alice has to do this whole process, but in reverse, right? So there's always this forward and reverse in these algorithm. Any questions? All right, great. All right, so that was kind of, very interesting. Definitely CBC will implement the code on Thursday. Now, the next thing I'm going to do is we're going to start the description of DES. All right, so DES is the data encryption standard, right? So the precursor, this is still available, right? You go to many pieces of hardware, computers, and things like that. You will see maybe a little drop down with DES still in there. Okay, it's the most studied. So it's in the slides. If remember, there's some slides that I've made available, and DES is the most studied, I believe, encryption algorithm. Okay, because remember, the key thing with these encryption algorithms, nothing about them is, everything is known about these algorithms, right? So it's not about security through obscurity. Instead, they are highly studied. And you just count on the fact that if you don't know the key, they will be secure, right? So DES, of course, has been broken now since the late 90s. And then because of that, AES came about, which is much more secure. And so that's kind of where we are. But we're gonna start with this. So first, I need to give you a formal definition of what a block cipher is, and then from because that's actually the underlying. And you'll see that these definitions are really simple, right? So what was the definition of a hash function? Do you guys remember? It's a mapping of what? Variable length to fixed length. Very simple, right? So, and that's essentially what you want, something that's very big and like a book or a movie or whatever it is, and you map it through some function, right, into a fixed length sequence of bits, which we know as a hash. So now I'm going to do kind of the same thing with block ciphers, and I'm going to provide a definition for it. And it's a very broad definition. And then, of course, people start to implement algorithms that meet these requirements and so on. All right, so let's move on to defining what a block cipher is or should be as we advance into defining DES. So what are block ciphers? So the key idea is that we once again map bits to bits, right? So that's essentially, we're always thinking in bits. So it's a mapping from bits to bits, but it's going to be like this. So a block cipher is, or let's say maps, block cipher maps n bits of input to n bits of output. Do you see that? That's essentially like the simplest definition, right? So maps is going to do n bits of input to n bits of output. So that's it. So what you can see, this is what we've been doing, right? So in a way, we have been doing that. We just didn't have a definition of it. Why? I had n bits here, right? You agree? N bits of input. And what did I end up with over here? N bits of output. Everything that happens in between is like, I don't, you figure it out. But for this to work, you start with N bits and you arrive at N bits. Okay? So that's essentially what's the definition is. Oops. There we are. All right. So now the algorithm then for a block cipher, we can define it more formally. We have a plain, I'm going to use a different color here. Green. All right. So now this, we have a plain text block. Plain text block of n bits of n bits of n bits. And this is going to go through, we're going to have a an encryption and a decryption function, just like before, right? The same thing we've been having. This is going to take in a key, and the key doesn't necessarily have to be n bits. It can be k bits, in fact. K bits. That means power. All right, so the key, so there's several algorithms that oh, and I haven't finished this. So then, of course, over here, what do we have? We have the cipher text block. So the cipher text block, which is going to be what? Of n bits, right? So n bits. Okay, so that's pretty important in this process. So these are, of course, the algorithms that we're going to be using and however you want to define them. So let's look now at some of these classic examples. So we have, of course, des. There's actually something called triple des. And then there's AES. The one is the data encryption standard, and then the other one is triple data encryption standard, and then the other one is the advanced encryption standard. Okay? Um, so these have certain characteristics. So they'll have like block sizes, key sizes. So just to give you an idea, so something like DES and triple DES would use up for the block would use something like 64 bits. Whereas for AES, you use 128 bits. So we'll see later on in the slides that essentially, having a larger block, right, might provide more security. So that's the idea. Okay? So essentially, you can see it grows a little bit. And that depends on computing power. The more powerful the computers are, the more the bigger the things the blocks can be, but also there are limits. Even with our powerful computers today, you guys will see that these algorithms can take a long time to process. That's why we want to use the XOR operation, especially for confidentiality. So remember, if we're encrypting a whole movie, we use XOR. If we're sending the key, because it's just a little piece of information, then we can use something like RSA. RSA is much slower than a block cipher. Do you see that? So that's pretty important that the XOR operation is efficient. All right, so now we're almost ready to start defining the data encryption standard. We're just going to define one more concept before we get there called a round key. All right, and you can see how this just is. It's an expansion of the keys. So instead of using one key all the time, you can actually expand your original key into multiple keys. So you can think of the key that you provide to the algorithm as simply just a seed that you give to a function. So this is a little bit similar to the pseudo-random key function that we talked about last week. Do you guys remember that? Right? So you can think of the pseudo-random key, right? You give it a key, and then from there you can generate other keys based on some algorithm. So that just provides more variation. So that's called a round key. So block ciphers are typically built by iteration. So you guys know that. You get a key, and then the next step usually is you expand the key into a sequence of keys called round keys. All right, so this is going to be the next topic we talk about, round keys. Round keys are essentially a sequence of keys. Round keys are a sequence of keys, um, expanded from the original key. From the original key. And then I'll just say such as a PRG. right? And you guys already know what a PRG because we covered this last week. So a pseudo-random generator. I will provide some code for that, but essentially that's the idea. Does that make sense, guys? Yeah. All right, so just a determinant. Remember, a pseudo-random generator is a deterministic algorithm, but you provide some random key, and from it you can generate all kinds of things. So now you will have a set of keys instead of one key. So then the message is going to be encrypted using these keys, and I'll provide once again a diagram just to give you an idea of how that process is done. And these are you're going to have these things called round functions. So each round function is an XOR operation using one of these keys. All right, so let's take a look at that idea. So this is a simple example. There's something that we could also implement with our XOR code. So imagine we have, a block. So now we're going to have a block. I'm just going to denote it as M, remember, and I'm going to say that it's 128 bits. Okay, so that's the block. Remember, a block cipher is anything that maps n bits into n bits. So here n is 128. I'm going to have an original key, right? And this key goes into some kind of pseudo random generator function, right? And that pseudo random generator function then produces a set of keys, however many you want, 16, for instance. It's a good number, right? So then that's going to be key 1, key 2, say key 3, and these are the so-called round keys. And I'm going to do this all the way to key kn, such as 16. Kn, okay? Or m, actually. I'm going to use the letter m here because I'm using n for the number of bits in the block, and they are definitely different. Okay? So then this, of course, what happens here is the m message goes in here with the first key, and you have an XOR operation, just like before. Let me redo. Okay. Just like that. Do you guys see that? That's going to produce, so this is your first round, all right, of the message with key 1. What does this produce? So I'm going to do it like that. This produces M1. But actually, this is no longer just M, right? Because that would be a message. So let's change the letter to, let's say, C1. An encrypted version of this. And then now this same block can be XORed with K2. You can see that essentially. So what happened there? It's the same operation, right? But I just added more complication to it. Do you guys see that? Instead of just one key and using it all the time, how about I use a deterministic algorithm and generate 16 different keys from that same one? Keep in mind, if you do this forward, you have to do it in reverse, right? So that's always the key characteristic. All right, so then I do K2, and this one produces C2. Notice here, though, I'm just encrypting the same message. This is not two ciphers, right, or two pieces of the plain text. This is just still the same plain text of 128 bits, and this is C2, and then this one becomes the input here, and that is XORed with key 3. Right, and then we repeat this process. This would produce, let's call it C, and I like to call these maybe we should say MC1, but this should be fine. So C3, and now dot, 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 until this, whatever comes in is XORed with the last one. And then at the end, so I would have this comes in, let's say from over here, with this key, and I have now my final CM. And that is actually the cipher just for this one block. Do you see that? So we performed 16 rounds. So think about that. That's why the XOR makes sense, right? Because it's fast in the computer. Imagine if this was an algorithm that took a long time to run, and now we do it 16 times. So it's gonna literally slow down everything. Got it? All right. So any questions on round keys? Make sense? All right, perfect. So now this is another thing we could implement in Python. All right, now I think we have a lot of the pieces necessary so we can start looking at the data encryption standard. Okay, so DES, um, as I said, is essentially something like this. We're just adding more complication. And at the heart of DES, there's something called the Feistel network, which is like a very elegant little graph that they use for the encryption, a little bit similar to this idea of round functions. Okay, so let's go ahead and jump into the data encryption standard. So remember, again, this is still symmetric encryption. This is still symmetric encryption. This is still symmetric encryption, and this is still block ciphers, and essentially for confidentiality. Okay. All right, so let's talk about DES. So this is the algorithm. This actually, obviously, it's a more complex algorithm. So this has several steps. All right, so it'll take us a little bit to go through it, okay? But it starts here. So the data encryption standard, DES, data encryption standard. So how does this work? So basically, there's like a group, NIST, like some group, right? And they want to achieve a goal, right? They want to have security. And so they make a call for proposals. That's actually what's happening with quantum right now. There's a quantum ready algorithms committee, right? And they have a call right now. So if you guys, let's say that you love this stuff and you're like, I'm going to do the next quantum one. So you start working on it and you go to their call for proposals and you read what they want, right? Essentially algorithms that, encryption that cannot be broken with a quantum computer when they exist. And so this is something that everyone's really nervous about. And so they put out the call and then people study, like there's these principles, maybe math principles, etc. And then they figure out, okay, we think this is going to be secure. Here is how it would work. And it's like a theoretical description of it. And then other teams come in and they start implementing it in C++ or whatever it is. And then they submit their solution and then it gets tested, right? It's going to constantly, people are going to try to break it essentially. And if they can't break it, then, that's good because it means it'll probably become recommended at some point. But if it's broken, which has happened with a lot of these quantum ready algorithms, then that's it. It's done. And it becomes just another research project that people may learn from, but it wasn't the solution. Okay. So that's kind of what happened with the data encryption standard. So you're talking about the 70s here, right? With the data encryption standard came about from IBM in the 70s. It worked for a while. It was broken in 1997. Okay. And so this has been the evolution, right? So let's start talking a little bit about that. So I've said that the data encryption standard is called DES. We've already defined that is, we're still using the definition of a block cipher, which I already stated to you guys. Oh, I skipped the page. Which was this, right? Maps n bits to n bits, and I already wrote essentially this. This is what we would go, this is what they want, the call for papers. And then now somebody comes in and proposes, okay, here is my solution to this, and I'm calling it DES or whatever you're calling it. All right, so let's just give it some historical things. So done at IBM, okay, around the 1970s, 1970s, okay. In 1997, it was broken. Was broken. But it was broken by exhaustive search. All right, so exhaustive search. So they essentially had fast enough computers. So what does that mean? It means that, you know, they would grab it, run it through a computer for a little while, and boom, I just broke it, right? And they were able to measure the time that it was taking to break it. So everyone maybe got worried because a lot of things were being done with desks, like banking and things like that. So what did they do? Which is kind of funny, but what they did quite simply is they invented triple desks. What do you think triple desk does? It's essentially desk done three times. Do you see that? So take something, goes into desk, comes out, and that would take maybe, let's say, 1 minute. But so what do you need? You need, to increase the amount of time that it takes to break it, right? So let's say 5 minutes it would take. So then now if you do triple desk, it takes you 15 minutes to break it, right? If it took 10 minutes to break it, then now it takes 30 minutes to break it. Do you see? So it wasn't really a great solution. I imagine this is what would happen if quantum breaks some of these algorithms. They're going to panic and just increase the amount of encryptions just so that it takes longer to break it, or I don't know, something like that. Who knows with quantum computers? But this definitely did happen with DES. So that's why triple DES exists, and we'll discuss triple DES later. Okay, but yeah, so this is the idea. So this happened in 1997. We will discuss, of course, the data encryption standard out, and you'll see that it's not trivial. It's actually quite complex and elegant, but it was broken. In 2000, so in around 2000, they did the same thing, a call for proposals. Um, we need, something that, the keys need to be bigger. It shouldn't be broken so easily, those kinds of things. And then they created or they adopted something called the Advanced Encryption Standard, AES, which is what you've also seen in your OpenSSL homework, right? I'm sure you noticed you did AES, CVC, something like that. So you're just using that more advanced encryption. This one uses matrices and vectors, so it uses like a field of math called linear algebra. So what that does is like it's very interesting. So instead of just encrypting like one block, you're doing 64 blocks in parallel at the same time, right? So if you guys have taken machine learning, you remember those tensor operations. So similar to that. So a matrix instead of just one vector. All right. Oops, what is that? Oh, okay. Still running though, right? Yeah, okay. So I assume it's still running. Um, Maybe just to be on the safe side, let me end this video and I'll start